You finish a brutal chemistry calculation, confident you nailed the math. Then you get your exam back, and the grader slashes your final answer. The numbers on your calculator screen are useless on their own. To get full credit, you have to format those raw outputs using correct significant figures, scientific notation, and exact unit conversions. We are going to lock in a 3-step process to get this right every time. Grab a pencil and a messy piece of raw data to follow along. Mastering this formatting framework is your best defense against losing points on technicalities. Let's make your final answers bulletproof. Step 1 is determining significant figures. We can skip the confusing textbook rules by splitting all numbers into 2 clear categories: non-decimal numbers and decimal numbers. For any non-decimal number, look at the digits. Find the first non-zero number and draw a bracket connecting it to the last non-zero number. Now count everything trapped inside that bracket. If you bracket 6 digits, your measurement has exactly 6 significant figures. Now let's look at decimal numbers, which require a slight adjustment to the trick. Start your bracket at the first non-zero digit, but this time, stretch your bracket all the way to the absolute final digit, even if it is a 0. Tally up the numbers inside. If there are 3 digits captured, you have 3 significant figures. This visual method entirely bypasses the need to memorize standard rules about leading or trailing zeros. Identifying significant figures separates the mathematically certain data points from useless noise, ensuring you only report what you actually measured. Step 2 is managing scale. Chemistry deals with measurements so massive or incredibly tiny that writing them out in standard form wastes valuable time on an exam. This is the Earth. Its mass is approximately 6 septillion kilograms, a number with 24 digits. Writing that out by hand is physically unmanageable. Instead, we compress this down to 6 times 10 to the power of 24 kilograms. We apply this exact same logic to the opposite extreme, like measuring the microscopic diameter of an atomic nucleus. Here, we pull those zeros back, tightening the measurement into 1.7 times 10 to the negative 15 meters. Scientific notation preserves the specific significant figures we just found while hiding all those useless magnitude zeros. Step 3 is dimensional analysis. Now that your number is compressed and properly formatted, you have to translate it into the specific target units requested by your grader. The most reliable way to convert units is by establishing a ratio. If we want to convert meters into kilometers, we set up a pathway using the fact that there are 1,000 meters in exactly 1 kilometer. Take a raw measurement, like 3,045 meters, and divide it by our ratio of 1,000 meters per kilometer. This gives us 3.045 kilometers. Notice how the mathematical operation physically cancels out the old meter unit, leaving only the target kilometer unit behind. That works perfectly for distance, but temperature conversions trip up a lot of students because the logic changes slightly. When converting from Celsius to Kelvin, we do not multiply or divide. Instead, we use addition. Take 35 degrees Celsius, add 273, and you get exactly 308 Kelvin. Proper unit conversion aligns your math with physical reality. Submitting a naked number without a final unit is a guaranteed way to get marked down. Compare the chaotic, raw data you started with against a tightly notated, perfectly formatted final answer. You extract the significant figures, compress the scale with scientific notation, and convert into the correct units. Check the video description below. We have put 3 practice problems down there for you to immediately test this framework. Proficiency in chemistry finds the correct answer, but technical precision secures the grade. This framework ensures your hard work survives the red pen.